In Chapter 6, Section 1, we're going to cover perpendicular and angle bisectors. I know we've talked about bisectors before. We've had segment bisectors and angle bisectors, and we're going to get into a little bit more detail about it in this section. Again, first of all, a perpendicular bisector by definition is a segment, a ray, a line, or a plane that is perpendicular to a segment at its midpoint. So in other words, all of these things here, the segment, the ray, the line, or the plane, okay, can cross a segment, let's say segment AB, okay? It can cross it, but when it crosses it, it's going to cross it. Number one, it's going to be perpendicular when it crosses, meaning that when, for example, this is line CP crosses segment AB, it will cross at a perpendicular intersection point, which means it'll cross at a right angle, and then right angles, you know, are 90 degrees. So it's going to not only be perpendicular, but it's also going to cross at the midpoint. So two things are going to happen, or two things are you're going to know every single time you know that something is a perpendicular bisector. You're going to know that it crosses at a right angle, and you're going to know that it cuts the segment in half because it crosses at the midpoint. So it cuts segment in half, or even better, into two congruent segments, right? Because as soon as it cuts it in half, you know that AP is going to equal BP. The other thing we're going to learn about, and first we want to talk about the definition. We want to address this term here, equidistant. When something is equidistant, think of it as equal and distant being distance. And so it is something that is equal distance from some point or something else. Okay, and so we'll get into the topic of that in the upcoming slides. So, the perpendicular bisector theorem. Again, we know what a perpendicular bisector is. In this picture, we know that our perpendicular bisector is line CP. We know that the segment it's bisecting is the segment AB. And the theorem says that in a plane, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So what it's saying is, if this point here, point C, for example, if that point is on the perpendicular bisector, and we know that it is. How do we know it's perpendicular bisector? Well, perpendicular, and it cut AB into two congruent segments. So yes, this is definitely the perpendicular bisector. Any point that lies on it will be equidistant from the endpoints. That means that this segment from C to endpoint A is going to measure the same length as the point from C to endpoint, as the line from C to endpoint B. It's going to be equidistant, and that means any line I draw. Again, notice this red dot. Let's call this point D. DB is going to be the same length as, well, that's a terrible line, isn't it? As DA here. Okay, and so those two lines, even though I drew them terribly, they're going to be equidistant as well, which means those two line segments will have the exact same length. So again, that's a lot to know, and that's a really big deal, because as soon as we know that something is on the perpendicular bisector, we know we have segments of equal length. And remember, we're always trying to prove congruence. Equal lengths, equal angles, that helps us to identify lots of information. Now, the converse to this, again, remember, it's sort of backwards. So if the original says that if a point lies on the perpendicular bisector, then it is equidistant from the endpoints of a segment. Well, this is telling you then that if a point is equidistant from the endpoints of the segment, then it must be on the perpendicular bisector of the segment. So in this one, you're given the opposite. Notice you're given a segment. Here's our segment, you know, AB. And we have this point over here, point D, and we notice that AD is congruent to BD. What that means is that point D must be on the perpendicular bisector. So right now, notice that CP is definitely the perpendicular bisector. This is perpendicular. The segments are cut into equal parts. So if I extend this, I know that D is on line CP. It has to be because of this converse. So for example 1, you're given that BD is the perpendicular bisector of AC. So BD is the perpendicular bisector of AC. So AC is the segment that was here before, and BD is the perpendicular bisector. So I already know if it's the perpendicular bisector, I know it hits the segment at 90 degrees. And I know that the distance from this point on the perpendicular bisector to the end point, DC, is going to be the same length as segment DA. So this and this are congruent, which means I can find what x is. I know that 5x is going to equal 3x plus 14. I know that because I know, again, that AD is going to be congruent to CD. And so now I can plug in what AD equals, what CD equals, and I can do the math. So when I subtract 3x from both sides, I get 2x is 14, and when I divide by 2, I get that x equals 7. So that's an answer. However, they want AD. And so again, I know that AD is equal to 5x. And so if x is 7, then I know that AD equals 35 units, whatever those units are, centimeters, millimeters, inches, whatever. But AD is 35. In example 2, they want me to use the diagram and the given information to find the indicated measure. So I'm going to go one at a time. So in number 1, they tell me that line ZX is the perpendicular bisector of WY, which means that it's perpendicular here, but it also means that WX and XY are going to be congruent. In the drawing, it also tells me that YZ is 13.75 units long, and it wants to know what this side is. Well, again, if ZY here, if this is the perpendicular bisector of segment WZ, then I know that a point that lies on the line, I know that, for example, point Z lies on the perpendicular bisector. It's going to have the same distance to W as it's going to have to Y. So ZW is going to be congruent to ZY. If ZY is 13.75, then ZW or WZ is also 13.75 because they're congruent. So in this problem, I know again that WZ is congruent to YZ. So then WZ must equal 13.75. When I go to number 2, it gives me new information. So let me sort of erase this, right? Okay. So in number 2, I've got ZX is the perpendicular bisector of WY. Again, same thing. WZ equals 4n minus 13. So I know this and this are congruent. And YZ equals n plus 17. And it wants me to find the length of YZ. Well, again, I know that WZ is going to be congruent to YZ. WZ is 4n minus 13. YZ is n plus 17. So I'm going to solve for n. I'm going to get 3n minus 13 equals 17. I'm going to add 13 to both sides. I'm going to get 3n equals 30, which means n is 10. So again, they don't want n, they want YZ. So YZ is n plus 17. So 10 plus 17 equals 27. So I know that YZ equals 27 units, whatever those units are. And then the last problem I'm going to solve is going to be number 3. Let me again erase this information, and I'm going to start here. In number 3, it says find WX when WZ equals 20.5 and WY equals 14.8. WY is the whole side, and YZ is 20.5. Again, once they tell me that these two are the same, okay, again, I know that they didn't tell me that it was the ZX was the perpendicular bisector. However, once I know that the point on this line is equidistant to the endpoints here, I know once again that that's going to be, it's on the perpendicular bisector. And what that means, I know that these two pieces, this little section here and this little section here, are congruent. If the whole side is 14.8, I know if I divide it by 2, I'm going to get the length of each half. So I know it's 7.4. So what I know then is that this piece here is 7.4 and this piece here is 7.4. And again, since they're asking me for WX, I know that WX, which is this piece right here, is 7.4. Angle bisector theorem. So now we're not talking about segments, we're talking about angles. And we've talked a lot about angle bisectors in the triangle chapter. We know that, well, let me just tell you the theorem. If a point is on the bisector of an angle, then it is equidistant from the two sides of the angle. So let's think about that. First of all, the angle bisector, let's identify it here. Initially, I'm starting out here with this angle. I'm starting with this large angle ABC, okay? It goes from point P up, B to A to C. And this large angle, notice there is this bisector here, this ray that has bisected the angle. AD is a ray that bisected it. Now, we've learned a while ago that an angle bisector cuts it into equal parts. And so we know that if it's the angle bisector, we know that angle BAD is going to be congruent to CAD. The small angles are going to be half of the large angle. We know that from before. Now this is taking it one step further. We're saying if we happen to have a point that's on the angle bisector, then that point is equidistant from the two sides of the angle. Now remember, when we're finding a length or a distance, we have to do a line that meets it or is perpendicular to the other one. That's how we find an accurate distance or length. It's the shortest distance from the point to the end of the angle. And so again, I have to do a line down that is a right angle, but I know that once I do the correct line, I know this piece is going to equal this piece. And that's what the theorem is telling me. That DB has the same length as DC. The converse is going to tell me the same thing. It's going to tell me in reverse. The converse is going to say if I happen to have a point on a ray and that point is equidistant from the sides, okay, notice that DB is congruent with DC, then that point must lie on the angle bisector. And so if it lies on the angle bisector, then you know that these two angles formed here are congruent. So in the first one, you know the angles are congruent, you know it's the bisector, so you know the lines are equidistant. In this one, in the converse, you know the lines are equidistant, which means it must be on the bisector, which means the angles, the conclusion for me is the angles are going to be congruent. Okay, so let's again look at what we've got and let's try to figure out how we can apply this. If I look here, I notice that this angle and this angle are congruent. So once I see that both angles are congruent, I know that this ray right here in the center, I'm going to put it in yellow, that this ray must be an angle bisector. And once that I know that it's the angle bisector, then the theorem tells me that this segment here is going to equal this segment here. So X must be 15. And that's all they want to know. In B, I see here that I've got these two angles, this angle and this angle, right? I don't know what those are. I don't know that they're congruent. So I'm going to look over here at these lines that have been drawn from this ray over to the side of the angle. And notice that it's perpendicular and it's congruent to the other one. If those two lines are congruent, then I know that this point lies on the angle bisector, which means this angle must equal this angle. So I know that 3x plus 5 must equal 4x. I think it's a 6. I'm not real sure, but it's either a 6 or an 8. I'm going to go with 6. I'm going to subtract 4x from both sides. I'm going to subtract 5 from both sides. And I'm going to end up getting minus x. This cancels, and I'm going to get minus 11. So x equals positive 11. And again, they don't want to know the angle measures. They only want to know the value of x. So I can stop there. Now I go to C, and again, I see the lines. I see the angles. What I know is congruent are the angles. I know that this angle here equals this angle here. That means that this line is definitely the angle bisector. And if it's the angle bisector, I know that this segment from here to here is going to be congruent to this segment from here to here. So I know that 5x must be congruent to 6x minus 5. Subtract 6x from both sides. Minus x equals minus 5. So x equals positive 5. And that's the final answer there. Again, these are using the theorems, okay? So if it's the bisector, then these are congruent. This is the angle bisector theorem, okay? This one, if the lengths are congruent, then it must be an angle bisector. So the angles are congruent, right? And so this would be the converse of the angle bisector theorem, okay? And then this last one, again, here we were given that the angles were congruent, so this is the angle bisector theorem. So when you're given the angles are congruent, it's the angle bisector theorem. When you're given that the lines are congruent, it's the converse. And then the last one says they want you to write an equation of the perpendicular bisector of the segment with the endpoints. P is negative 2, 3, and Q is 4, 1. That's a little bit confusing, right? So basically they want you to, you have this segment here, okay? You have segment PQ, and they want the equation of the perpendicular bisector of that segment. Well, first of all, we're going to have to do a little bit of work here. We're going to have to first identify what the midpoint is of this segment, right? Because remember, the perpendicular bisector is going to go through that midpoint. Now, the midpoint is written there as 1, 2, but you might not always have that. I feel like the answers are written here on this one where yours is a blank copy. So how did they come up with m equals 1, 2? Well, again, I need to remember the midpoint formula. If I want to know what the midpoint is of point P up here at negative 2, 3, and the midpoint of point Q at 4, 1, remember the midpoint is the average of my x's. So I've got minus 2 plus 4 divided by 2, that's the average, and the average of my y's, 3 plus 1 divided by 2. So I come here, this is 2 over 2, and this is 4 over 2, and so this is 1, 2. So I know the midpoint is 1, 2, and that's right here. That's how we got this m value, okay? Yours is probably blank. So now I know, remember, I know that the perpendicular bisector has to cross through the midpoint, so I found that. And then a perpendicular line, I know that the slope is the opposite reciprocal of the original slope, right? Reciprocal of the line. So again, now I've got to think of what is the slope going to be of the line that goes through that goes through PQ, or that's the perpendicular bisector of PQ. Well, what is the slope of PQ, first of all? Okay, well, the slope of PQ, I could count if I wanted. I know the slope is rise over run, and from P to Q, I'm going down 2 units, and I'm going to the right 1, 2, 3, 4, 5, 6 units. So I know the slope of PQ is negative 1/3. So the slope of the perpendicular bisector right, is going to be the opposite reciprocal of that, which is going to be positive 3 over 1, or just 3. So I know my slope is 3. So I have now, if you think about it, I have to write the equation of a line that goes through 1, 2 and has a slope of 3. And again, we learned 2 methods to do that. You could either use the point slope formula, okay, which was x minus x1. So we've got y1 is the y of our midpoint, which is 2, m is 3, and x1 is the x of our midpoint, which is 1. Then I would distribute here, 3x minus 3, and I would add 2 to both sides, and I would get 3x minus 1. And that is the equation of the line that is the perpendicular bisector of segment PQ. You could also use the other formula where, remember, we did y equals mx plus b, and you could plug in the y and the x from the midpoint. Y is 2, m is 3, x is 1, and you can use that to find b. 2 equals 3 plus b, minus 3, and you get minus 1 equals b. So again, if you know m is 3 and b is minus 1, then the formula is y equals 3x minus 1, or mx plus b. Either way, that's how you find it. So even though in my picture we have this red line and we have the equation and all that, I think yours is probably blank. What you would be given is just the original segment, and you would have to find everything about that red line. And so again, you're going to start by finding the midpoint of your segment, midpoint of segment. And then once you find the midpoint, you're going to find the slope of your segment. Okay, you're going to have to find your slope. And then you're going to have to find the slope of the perpendicular bisector, which is going to be the opposite reciprocal. And then you're going to use the midpoint you found and the slope that you needed, and you're going to then put it into either point slope or slope intercept form to find the actual equation. So there's a lot of work here, a lot of math required, but this is how you would do that.